Hello and welcome to my walkthrough of some vector calculation questions for electromagnetism. So let's get started. So our first question asks us to prove that del dot del cross fr equals 0, where fr is a continuously differentiable vector field. So the first thing I like to do is to write out what everything in the equation actually is. So fr is our vector field, which has components in x, y, and z, and del is the derivative in the x direction, y, and z direction, but to save me time, I'm going to be writing it like this, so don't get confused, it just saves me having to write the fractions. So the first thing we need to do is we need to find del cross fr, and this is just a cross product which looks like this. Now, those of you who know cross products, you know that it'll expand out to I times by this determinant minus j times this determinant plus k times this determinant. Now, timesing across the diagonal, minusing across the other diagonal, we get this bracket for our I component, this for our j component, and this for our k component. Now, you'll notice that in any of these brackets, the direction of derivation is not the same as the direction of the component of the field. So for example, in the first one, we have del y f z, which means that since it is in the z direction, it doesn't have any change in quantity over the y direction, so it goes to 0. And this happens for all of them, and they all go to 0, which is very handy for us because it means we get 0i minus 0j plus 0k. Now, this is quite obvious that this is going to go to 0, but just to be thorough about the whole thing, we're going to do del dot this vector, which comes out as dx 0, dy 0, dz 0, which all go to 0. So here we are, del dot del cross fr equals 0. Our next question asks us to prove that del cross del fr equals 0, where fr is a continuously differentiable scalar field. Now, as before, we can write out all of our things from the equation out like this, but notice that fr is a scalar field, so instead of having components of fx, fy, and fz, we have values of a, b, and c. And del stays the same as before, dx, dy, dz. Now, del fr is the same as del dot fr, which means you just times it into the bracket and you get dxa, dyb, and dzc. Now, we want to do a cross product of that now. So here we have del cross del fr, which looks like this. Now again, we times out the cross product and expand it to make it look like this, where we have our determinants of our submatrices. Now these determinants are formulated like this, where you have dy, dz, dc minus dz, dy, db, and again along the same things for all of them. Now you'll notice that in each of the brackets you have the same two directions of differentiation, just in different orders. So in the first one we have dy dz c minus dz dy b. Now, because of the fact that it's a continuously differentiable scalar field, this means that those are the same thing and they're equivalent, so they cancel. And you get, once again, 0i minus 0j plus 0k, and this equals 0. So here we have our answer, del cross del fr equals 0. In this question, we are asked to calculate del dot r, where r is a position vector x, y, and z. Once again, our del is dx, dy, dz, and our position vector is as has been said above. Now, all we need to do, very simply, is find the dot product of the two, which means you get dx, dy, dz dot x, y, z. And this is the result from that. Now differentiating x with respect to x gives you 1. Differentiating y with respect to y gives you 1, and z with z 1. So in total, our answer is 3. Fantastic. In question 4, we are asked to calculate what del dot z hat cross r is. Now we know what del and r is from the previous question, and z hat is just a unit vector in the z direction, so it is 0, 0, 1. Now the first step of this is to find out what z hat cross r is, and that gives a cross product that looks like this. And once again, expanding out our cross product, we get these results. And as before, we can expand the determinants to get I 0z minus y minus j 0z minus x, and k with 0y and 0x. Now these can be simplified very easily, and this gives us our vector form of z hat cross r. Now next we need to do del dot this result, and this is very simple, and you just do dx dy dz dot minus y x 0, and this is the result we get from that dot product. Now you'll notice that the direction of the differentiation is different to the value that's being differentiated. So for example, you have dx y and dy x. Because these are in different directions, you get 0 for the first value, 0 for the second value, and 0 for your last value. So the answer is 0. Now here in question 5, we are asked a very similar question. We are asked to calculate del cross z hat cross r. Now we know all of these starting points from last time, and in fact our first step to find z hat cross r is exactly the same as last time, and so we get the same result, which is minus y x 0. Now the difference this time is, instead of doing del dot this result, we are doing del cross this result, and that causes us to get this beautiful cross product. Now expanding the cross product out, we get these results, and expanding the determinants out, we get these results. Now you'll see that none of the components except the k component actually create anything, because the derivative of 0 is 0, and the derivative of x in the z direction is also 0, and same principles for the j component. So those guys disappear, and we are left with 1 plus 1k, or 0, 0, 2, which is our final result. Our final question asks us to calculate del of 1 over the modulus of r. Now del is just dx dy dz as before, and r is given by the 3D Pythagorean theorem, so the square root of x squared plus y squared plus z squared. And 1 over this is simply 1 over x squared plus y squared plus z squared, all square rooted. Now the question asks us to calculate del of this function. And so here is our del, here's the function, and it times this together to look like this, with components in the x, the y, and the z direction. But we need to find out what dx of 1 over r is, dy of 1 over r, and dz of 1 over r. What we can do is we can work through with x. So here is our expanded expression, and this can be simplified as the 1 over can become a minus power, and the square root can be a power of a half. Now in this form it's much easier for us to use, as we can apply the power rule. So our minus 1/2 comes out the front, and we take 1 away from the power, and then we times the whole expression by the derivative of the function on the inside. Now our front term can simplify slightly to become minus 3 over 2, and the back end, each component gets derived by x. This is simply taking away the negative indices to get a 1 over, and taking the derivatives of the back end, we get 2x plus 0 plus 0. So we can times the 2x into the fraction. Now notice that 1 over r is the same as 1 over the square root of x squared plus y squared plus z squared. We can simply sub this expression in to get minus x over r to the 3. So we now know that dx of 1 over r is minus x over r to the 3. And we can say that the same will be for y and for z. So substituting this into our expression above, we get minus x over r to the 3 minus y over r to the 3 and minus z over r to the 3. But we can take a factor of 1 over r to the 3 out, leaving us with x, y, z. But you'll notice that the position vector is x, y, z. And we can simply substitute this in to get minus the position vector over the cube of the r. And that is our final answer. Thank you very much for watching this video. I hope that it's made these vector calculations a little bit clearer. If you spot any mistakes I've made during this video, please let me know and I will try and correct them. Thank you very much.